Right, good morning everybody. So, in today's fifth lecture, I want to do three things. I want to work through a complete normal modes example in the general unequal mass case. I then want to discuss transverse vibrations, because the vibrations we've been discussing so far, insofar as they involve springs, involve the spring moving, the mass moving along the line of the spring. In order to discuss waves, we need to discuss that kind of motion, and that is less obviously linear. And in fact, it is not so linear. The linearity of the vertical system, as we have it here, depends only on the linearity of the spring. As long as the spring force is a linear function of the displacement, the system is linear. In this mode, it's amplitude dependent, and we need to have small amplitude for it to be linear. And then with that, I can make the transition to waves, which I may or may not get onto at the end of the lecture. So the first example I want to talk about is the general case, which is more unequal mass. And the system I'm going to be looking at is the one without the coupling spring at the bottom. So it's that system. But these masses are both 50-gram masses, but I'm going to model a system where this mass has 3/2 times the bottom mass. So the mass matrix is going to be m times 3, 0, 0, 2. So the masses are 3m and 2m at the bottom. The K matrix is the one that we've used quite a lot of times now. K, 2, minus 1, minus 1, 1. And the initial displacement, I'll stick with the relatively easy case of holding that mass fixed, moving this one down by a distance a, and then starting from rest. So x of 0 is 0a, and v of 0 is 0. So that's the problem that I've set myself. The eigenvalue equation is k 2 minus 1 minus 1, 1 is C is lambda m times the mass matrix 3, 0, 0, 2. C. And I'm going to divide through by k so that all the constants are in the same place. And then I'm going to take this over to the other side to give me 2 minus 3. I'll call this quantity here. No, but I'll call that quantity there alpha. 2 minus 3 alpha minus 1 minus 1, 1 minus 2 alpha. So that is the determinantal equation that determines the eigenvalues. And that gives 2 minus 1 is 1, minus 3 alpha minus 7 alpha plus 6 alpha squared is 0. And obviously I've chosen the numbers so that this came to be easy to be factorised. So that is now 1 minus 6 alpha, 1 minus alpha equals 0, and so alpha equals 1 or 1/6. And so lambda over m, lambda is k over m times and k over 6m. Okay? If we put those back into the equation for the eigenvectors, we get, so let's do the fast mode first, which is lambda, m lambda over k equals 1. So alpha in that case is 1, and so that's minus 1, minus 1, minus 1, minus 1, c equals 0. So we could choose c to be, for example, minus 1, 1. And for the slow mode, we get 2 minus alpha is now 1/6. So we get 2 minus 3 alpha is 2 minus a half is 3 halves minus 1 minus 1. And then it's 1 minus 2 alpha, which is 1 minus 1 minus 2 over 6, which is 1 minus a third, which is 2/3. C equals 0. So the elements of C are in the ratio of 2 and 3. So I could choose C equals just 2, 3. So if you put all that together, we've got lambda omega squared C transpose MC C transpose x of 0. For the slow mode, we have k over 6m. So wonder why I wrote that down, because they're the same. C is 2, 3. So this C transpose MC is 4 times. Where's my maths? It's 3, yeah, so it's 3 in the top left. It's 2, 3 times 3 times 2, 6, 6, which is 12 plus 18, which is 30, 30n. And C transpose x of 0 is just, sorry, that should be 3 transpose m x of 0. All dot products have m's in between, so that is 2, 3 times 3 times 0 is 0, 2 times 0 is 2a, so that is 6a. And then for the fast mode, we have k over m minus 1, 1, and then we have 1 squared times 3 is 3, plus 2 is 5, m, and this number here is minus 1, 1 times 0, 2a is 2a. So those are all the elements of the solution. So putting it together, we have x is, for the slow mode, it's the amplitude of the oscillation is that. Actually, there's an m missing there because we've got the mass matrix, so we do need an m there. It's that. The amplitude of the, so this is the slow mode. The amplitude of the oscillation is 6 divided by 30 is 1/5 is a over 5 cos omega 1 t times the eigenvector, which is 2, 3. Sorry, it's not. Yes, it is. Plus, and for the slow mode, it's that divided by that, which is 5a over 2 cos omega 2t times minus 1, 1. Sorry, I did that upside down. That should have been 2/5. 2a over 5. Now, let's just check, before we go any further, that reproduces the initial conditions. So the top element here is 2a over 5, and here we have minus 2a over 5, so that's reassuring. And that gives us 3a over 5, and that gives us 2a over 5, which add up to 1. So that's all correct. So that's the complete solution. So it is just relatively straightforward. It's just slightly more complicated than with than if M is just a number that we can move around instead of being a matrix. If we look at the energy, both the potential and the kinetic energy split up into sums over modes, and because we're starting from rest, there is no initial kinetic energy, and so the modal decomposition of the potential energy at t equals 0 is equal to the modal decomposition of the energy at all times. So I just need to work out the energy in each mode, the potential energy in each mode. So E is sum over 1, 2 times, and this worked out to be, well, we can actually do it, can't we? X is C1 F1 plus C2 F2. So here, so that's C, and this bit here is F. And so that is C I transpose K C I F I squared. And I'm going to put in a naught in there because I want to evaluate it at t equals naught, and that's actually just, well, so the cos is just going to become 1 there. So here, KCI is MI, so that's CI transpose MC times the eigenvalue lambda, which is omega I squared, times Fi squared. So all the ingredients for the two modes we've already worked out. So for the slow mode, we get this is 6 sorry, this is 30m. That is k over 6m, and Fi squared is a squared over 25, which is k a squared 30, that's 5 over 25 is 5 k a squared over 5, which is and there was a half here, so which we need as well. And for the fast mode, yeah, that's right, M. So, yeah, the M's cancel there, of course. So that's a squared, yes, that's right, k squared over 10. So for the fast mode, we get that is 5m over 2. Omega squared is k over m. The amplitude squared is 4 over 25 a squared, which is k times 20 over 50, 2/5. 2k over 5. A squared. And if we just add those up, we get ka squared times 2 over 5 plus 1 over 10 is a half k a squared. And that, of course, is correct because we held this mass fixed and we stretched this mass by distance a, and so the energy that we put into the system was a half k a squared. So that's the correct modal decomposition. So the initial potential energies add up to the total energy in the system. So that's, roughly speaking, how you go through a complete normal modes problem with unequal masses fitting in the initial conditions. Obviously, I've done a case where the numbers worked out nicely, which they don't always, including the one on the problem set. So perhaps I should change to that one, actually, because the one on the problem set is full of root 5s. So now I want to discuss restoring forces when we move the mass not this way, but that way. Okay? And for this purpose, it's helpful to go right back to square one and figure out what the total, where the tension is coming from. So bear in mind that the initial spring was that long. That distance there is L0. That's the unstretched length of the spring. And for this purpose, it's quite important that it's very small compared with the stretch length. We can do exactly the same calculation for a stretched string, like a guitar string, which is what we'll be discussing when we come on to talk about waves on strings. However, in that case, of course, the amount that you stretch a guitar string when you tension it is really quite modest. It's a few percent or 10% or something. It really isn't very much at all. And so L0 in that case is a very large, well, is a large fraction of L. In this case, L0 is a very small fraction of L. I am, however, going to be discussing it as though it were horizontal. In this example, the tension in this spring is not the same as the tension in that spring, because this spring is supporting two masses and that spring is only supporting one mass. And I want the tension, I do definitely want the tension to be uniform throughout. So, and I'm also going to be imagining it to be fixed at both ends. So it's more like that problem. So the problem that I'm discussing is a spring, a mass, a spring, a mass, and an end wall. And both the masses are going to be the same, and all the initial tensions are going to be the same. And so this distance here is L, and that distance there is L, and that distance there is L. And I am going to displace that well, I won't draw the spring, I'll just draw the line of the spring to something like that, and that, and that. Okay? Actually, I haven't drawn that quite in the right place because it is rather important to this argument that the motion is just vertical. Okay? So we've displaced that by y1, and we've displaced that by y2. So it's, and virtually essential part of discussing waves on strings, that you assume that every element of mass only moves transverse to the line of the spring, transverse to the equilibrium line of the string. So we need maybe to just examine whether that's actually dynamically consistent. And we'll find that it isn't perfectly dynamically consistent, but there's a small correction. So first of all, I'm going to call these T0 at this stage, because I'm going to introduce the tension in this configuration as well. So here they're all equal to T0. So T0 is K L minus L0. It's the spring constant times the extension from the unstretched length. And here, so I shall have a T1, a T2, and a T3. And I'm going to introduce three angles, theta 1, theta 2, theta 3, and this one's negative. The sign of theta may matter at some point. So theta is positive when it's upwards. So T1, for example, is, well, the new length. The assumption is that that's just moved vertically, and so what was a straight line has turned into a right-angled triangle, and so the hypotenuse there is L sec theta 1 minus L0. So the length L has become L sec theta 1. And that would actually be true for all of those. So that's true for all I there. So let's have a look at the horizontal force on the mass M1. Because if I'm assuming that the masses move vertically only, this horizontal force must vanish. And we'll find that it doesn't quite, but it is quite small. Horizontal force on M1 is T2 cos theta 2. That's the force here, pulling it that way, minus T1 cos theta 1. So we multiply each of those by the appropriate, so that's F horizontal, which is K L minus L naught cos theta 2 minus K L minus L naught cos theta 1. And something rather interesting has happened. The big term in this equation, bearing in mind that L naught is quite modest compared with L, is the L's, and they cancel. So the part of the tension has gone up a bit due to the secant and gone down a bit, and the horizontal component has gone down a bit because of the cosine, and those two factors cancel. And so that actually cancels that. And so we're just left with K L0 delta cos theta. And strictly speaking, it's minus, if delta means 2 minus 1, as it usually does, which is, in a small angles approximation, that is plus K L naught theta over 2 delta theta I squared. So using a 1 minus cos theta approximation. So again, the cos theta doesn't differ very much on the two sides because of the small angles. So there are two factors that are making this small compared with the term that we've cancelled. One is that L naught is small compared with L, but the more significant one is that the angles are small. So this net horizontal force is, we'll find in a minute, is quite a lot smaller than the restoring force. So the acceleration in the vertical is quite a lot smaller than the acceleration in the horizontal, which means that the motion is predominantly transverse. Okay, so now, that was just to justify the assumption of vertical motion, and we find that it is an approximation, but it's not a bad approximation, because this is a small angle and it's appearing squared. So the total force on the two sides of the mass cancels to a very large extent. In the vertical, the restoring force is T sine theta. So F vertical is Fi vertical is Ti sine theta, which is where's my expression for T? K L sec theta minus 0 K L tan theta minus L0 sine theta. The approximation that we're going to make is essentially a small angles approximation, which replaces tan theta and sine theta both by tan theta effectively. So I'm going to write sine theta equals sine theta plus tan theta. Sine theta equals tan theta plus minus tan theta minus sine theta. Okay? And so Fi vert is K L tan theta minus L naught tan theta plus L naught tan theta minus sine theta. So this is the bit that I'm going to neglect, and what we're left with here is that the Fi vertical is K L minus L naught is T0. T0 tan theta is Y, well, is delta Y over L. Go back to the diagram. So each tan theta is the difference in the y coordinates at the two ends of the spring divided by the horizontal distance between them, L. So it's T naught over L delta y. And you have to figure out the right sign for delta y to get it getting it pulling the right way. And then the term that's being neglected, which has lost its k, is k L naught tan theta minus sine theta. The expansion of tan theta and sine theta both have a leading theta, and they differ in the cubic term. And so this is linear in delta y. This depends on y cubed. So So theta is roughly y over L. So this term here, actually, what is the cubic term here is minus a sec theta cubed. Anybody know what the cubic term there is? I'm off the top of their heads. I can't remember, but it's plus something, but I don't know what. So that is. It's almost certainly that's going to be a half, isn't it? So a half theta cubed. So it's something like KL naught y cubed over 2L squared. And that's got to be compared with this. So it's smaller by a factor of something like y squared over L squared and a factor of L naught over L. So it's quite a lot smaller, and we're going to neglect it. So putting all that together, we can now write down an equation of motion. So m d2 y1 by, I'll just do it for this two-mass system first of all, and then I'll generalize it to a much larger number of masses, is T naught over L so there's the force pulling it upwards, for which the delta y is y2 minus y1, and then there's the force pulling it backwards, for which the delta y is y1, and so this is y2 minus 2y1. Let's not have the m d2 y2 by dt squared is T naught over L. So that's got a force pulling it. So if I just redo the sketch briefly, then on this mass here, it's minus y2 and plus minus y2 minus y1, minus y2 plus y1. So that is T naught over L y1 minus 2y2. So putting it into my now standard form, m d2y by dt squared is minus ky, where k is T naught over L times 2 minus 1 minus 1, 2. Exactly the same as the vertical motion of that system, but with a different spring constant. It's T naught over L, whereas for that system it's just K out the front. So now I want to generalize this to a much larger number of particles. So I want to consider a very, very long spring mass system containing n masses. So we have a fixed end wall, we have an enormous number of masses, and another fixed wall here. So this distance here is n plus 1 L, and we have lots of mass separated by L along the way. And there's a uniform tension everywhere of T0. So the important point here, the sort of n that I'm thinking of here is 10 to the 10. Because what I'm thinking of is that these masses are atomic masses, basically. And this string consists of a very, very long string of atoms separated by a typical interatomic distance of 10 to the minus 10 meters. And it's my it's that long, so there are about 10 to the 10 of them. So the mass is now very small, L is very small, N is very large. That's the idea. And then this will enable me to make a transition into the consideration of waves on this string instead of considering it as a very large number of masses. So that's essentially a transition from a discrete to a continuum treatment of the system. So what's going on in this system is that when we displace these masses to say here, here, and here, so there's just 3 of them in the middle. It's only these 2 values of delta y that affect the force, the restoring force on mass I. And so in general, the equation of motion is m d2yi by dt squared, which is, well, let's draw it. Let's draw it as though they're both like that. So there's a tension here, T naught. The vertical component of that tension is effectively y over L times delta y over L. So it's T naught over L, y I plus 1 minus y I over L. And that's pulling it upwards. And then there's a downwards force, as I've drawn it there, minus T naught over L times yi minus yi minus 1. I've written the L twice here, haven't I? So I've written that as force and vertical component of force, and I'm approximating a tan by a sine, as I've already explained. So putting that together, we get m d2yi by dt squared is minus T naught over L 2yi minus yi plus 1 minus yi minus 1. Okay? And that's true for all the i's from 2 to n minus 1, and the only difference comes at the ends where m d2y1 by dt squared is T naught over L minus T naught over L y1 over L. So that's the case that we've already looked at with, so the mass at, well, so the one right next to the end wall has this equation of motion. So for y1, we just literally get that equation again. Which is that one. And for m d2yn by dt squared, we get effectively the equation of motion that we had before for y2, 2yn minus yn minus 1. And I've written the L's twice again. So we put that into a matrix. So the K matrix is something like T naught over L. So it's 2 minus 1, and then the next row has minus 1, 2, 1, and then I'm just going to, let's do that many rows. So that's 0, that's 1, 2, 3, 4, 5, so I want 5 rows. 0, minus 1, 2, minus 1, 0, 0, 0, minus 1, 2, minus 1. 0, 0, 0, minus 1, 2, etc. So all the way down at this end here, it terminates with minus 1, 0, so at minus 1, 2, 1, minus 1, 2. So the bottom corner. So we have a diagonal of minus 2's. We have a subdiagonal, sorry, a diagonal of plus 2's, a subdiagonal of minus 1's, a superdiagonal of minus 1's, and everything else is 0. So it's a very sparse matrix, and everything's very close to the diagonal. And that turns out to enable us to find the eigenvalues and eigenvectors for this matrix of order 10 to the 10. Because we go back to the general row, which we had up here. So we're going to, bearing in mind that the waves that we're going to impose on this very long mass spring system are very slowly varying compared with the intratomic separation, which is tiny. And so I can effectively, if these are the masses, I can put a smooth curve that they're effectively lying on a smooth curve like that. And so if I wanted to, I could replace yi as a continuous function y of x, and this is yi as a function of t, is a continuous function y as a function of x and t evaluated at the point il t. So I introduce a continuous function y of x and t for which the particular values of yi are just evaluated at, it's not very well written, il t. So the question is, what could this function be in order that, let's write down the eigenvalue equation. The eigenvalue equation is T0 over L 2y of il t minus y of I minus 1 L t minus y of I plus 1 L t. So that's the action of k on the vector y, and on the other side we're going to have the eigenvalue times y of il t. So what could the function be that if you combine twice the value at this point with the values at two neighbouring points on either side, and you get something that's proportional to the value at that point? So you think about the functions that you know about, and your attention gets drawn to trigonometric functions because they have difference relations of the right kind. So let me draw your attention, for example, to sine phi plus alpha plus sine phi minus alpha is twice sine phi cos alpha. So the combination of two neighbouring values is proportional to the value halfway between. And that's exactly the kind of function that we need in here, where these two, the combination of subtracting that plus that has to be something proportional to the thing that we're subtracting it from. So that's got the right kind of shape. So I'm going to make a bold guess. I'm going to suggest that y of I L t, well, it's not now a function of t because this is the eigenvector, isn't it? That c of IL is sine I phi. Okay. So then, if we put that into here, so, sorry, I wrote this for y. Really, this was the eigenvalue equation. This was really c, and it didn't depend on t. So I get 2c, which is sine I phi, minus sine I minus 1 phi, minus sine I plus 1 phi, equals lambda, and I'll take the T naught over L over the other side, T naught over L sine I phi. So I need to go on to the next board, and so if I collect the sine phi's on the left and everything else on the right, I get 2 minus lambda L over T naught. Actually, it would have been better to leave a bit more of a gap there. Sine I phi equals sine I plus 1 phi plus sine I minus 1 phi, which is twice sine I phi cos phi. Right. So, the nice thing about that is that everything that depends on I now cancels. So there's a sine I phi there and a sine I phi there. And so we've found something that does all the right, has the right shape to fit the eigenvalue equation for this very large matrix, provided all the constants come out right, which is 2 minus lambda L over T naught times sine phi equals 2 cos phi. Is that right? Yes. So, 1 minus cos phi equals lambda L over T naught. And so, lambda is T naught over L times 1 minus cos phi. So we've found a set of values for the vector which satisfy all the eigenvalue equation, all the lines of the eigenvalue equation with the general form, with this general form. So we're just left with the two exceptional cases at the two ends of the matrix. At this end of the matrix, we have so for I equals 1, we have T naught over, well, put that on the other side. We have 2 y1 minus y2 equals lambda L over T naught times y1. And so that is two sine phi minus sine 2 phi is lambda L over T naught sine phi. And that's always true. Well, the sine phi's cancel. And we get lambda L over T naught is 2 minus 2 cos phi, which is consistent with what we already had. So that's fine. So the only problem comes at the opposite end, where we have to do it for yn, and we find that that gives a condition on phi, but I'm not going to start that now. So I'll complete that next time, and I'll recap where I've got to so far. So the effect of this is that we're about 2/3 of the way through a transition from a very large normal mode system to a waves problem, and then I'll carry on tomorrow talking about waves. Thank you.